Okay, so 5.6, exponential and logarithmic equations and inequalities. And we're going to solve them. So our homework due on Tuesday. And I put here, remember solving any equation graphically, we want to see for what x values the expression on the left of the equation intersects the one on the right. So we can, again, once we have an equation, do it in Desmos, put the left side and the right side on different sides of different line items in Desmos and see where they intersect. So solving exponential equations symbolically. So isolate the exponential expression on one side of the equation, take the log or ln of each side of the equation and apply either the inverse property or the power rule and solve for the variable. Solving logarithmic equations symbolically, isolate the logarithm expression. On one side, you may need to apply the properties of logarithms. Exponentiate each side of the equation with the same base as the logarithm. And apply the inverse property a to the log base a of k is equal to k. Solve for the variable and check your answer here. So number 1 says, suppose that $1,000 is invested for T years at 8.5% compounded quarterly. Write an equation and estimate the time for P dollars to double. So I'm going to zoom in here. So we need this formula. A is equal to P parentheses 1 plus R over N to the NT. And so the 1,000 is our P. This 8.25 is 0.085 is our R. Compounded quarterly is N equal to 4. And we want our P dollars to double. So that means that A is equal to 1,000 times 2. So my A is 2,000. So substituting stuff in, 2,000 is equal to 1,000. 1 plus 0.085 over 4 to the power of 4 times t is the equation. And we're going to solve for t. So I'm going to divide both sides by 1,000. And on the left-hand side, I'm left with 2 is equal to 1 plus 0.085 divided by 4 is a nice decimal number, 0.012125 to the power of 4t. Okay, so we have an exponential equation. The variable is in the exponent. And so here again, isolate the exponential expression on one side. So I'm on step 1. Step 1 is done here. So I'm going to put here, all of this is step 1. And then step 2 says take the log or ln of each side of the equation. So for step 2, if you don't want to, what can I say here? In previous notes, I would say take the log ln of the base that you're using. So this is the base that we have right here. So I would like to say log base 1.02125, and I'm going to take the log 1.02125 of both sides. So that means that I'm going to, on the left side, that 2 is still there, and on the right hand side I'm going to have 1.02125 to the 14. And so here, these right here are inverses of each other, because 1.02125 to what power gives me 1.02125 to the power of 14? Well, the power is 14. So on the right hand side, I'm left with 14. And again, especially if math is in your future, this right here that I circled. Maybe I should have circled a little bit better. So hang tight. Let me undo here. Oh, darn. This what I circle. Nope, that's not what I wanted to do. This that I circled right here is saying 1.02125 to what power gives me 1.02125 to the power of 14. If I'm changing this logarithmic expression, just what I circled in pink, if I'm going to change that to an exponential equation, it's the base. And again, this number right here is that number right there. And everything here that's in blue is all of this in blue. So 1.02125 to what power gives me 1.02125 to the power of 14? Well, my question mark is 14. That's why right here on my next equal to sign, I can put 4t here. Another explanation is that log base 1.02125 of 1.0225 are inverses of each other. Some of you like to say cancel. And so we can say that this is gone and we're just left with the 14. But really, the right way of explaining it is this right here. If we were to change that logarithm, just the one in pink, to what I just outlined here in black in this black little cloud, the reason why we're just left with 4t is this right here. And so our calculators might not have a log base of 1.0215. So on the left hand side now, so now I'm going to the left hand side, I'm going to use the change of base formula. Change of base formula. So it's going to say the log of 2 divided by the log of 1.02125. And so the 4 and the t are multiplying. So to get rid of a multiplication, you're going to divide both sides by 4. And so my exact answer for t is log of 2 divided by the log of 1.02125, all of that divided by 4 is going to be equal to t. And if you do that in your calculator, you're going to get that t is approximately 8.24 years. Okay, the next problem. Number 2, suppose 1,000 is invested for t years at 8.5% compounded continuously. So here we need to use this formula. For continuously, we need this whole formula. And so this is still our P. This is still our R. And we want it to double, so that means that our A is equal to 1,000 times 2. So we still have here 2,000 is equal to 1,000 e to the RT. Divide both sides by 1,000. And I get 2 is equal to e to the RT. And so here my t is in the exponent. Oops, I forgot to substitute the r. So let me put that r in. It's 0.085. And since my base is e and my exponent is t, and is my variable, t is in the exponent. To get rid of an exponent, I'm going to take the ln of both sides. And why the ln? Because my base is e. So I'm going to take the ln of both sides. And so on the right hand side, again, all of this is technically asking you e to what power gives you e to the 0.085t. Well, since my bases are the same, my exponents have to be the same, and the question mark must be 0.085t. So on the right hand side, it's 0.085t. And again, some of us might just say, well, ln and e are inverses of each other, so we're left with 0.085t. But again, this right here is the more correct analysis. Okay, so on the left-hand side, I'm left with ln of 2. And so I'm going to divide both sides by 0.085. And I get that t is equal to ln of 2 divided by 0.085. And please check it on your calculator. Make sure you know how to get those decimal representations. T is going to be approximately 8.5 years. Okay, number 3. The percentage P of radioactive carbon-14 remaining in a fossil after 2 years is given by P is equal to 100 times 1/2 T to the power of 5,700. Suppose a fossil contains 35% of the carbon-14 that the organism contained when it was alive. Estimate the age of the fossil. Okay, so this 35% is the percentage of P radioactive carbon remaining. So this is our P. Okay, so 35 is equal to 100 times 1/2 to the T over 5,700. So I need to isolate the exponent and with the corresponding base, so the 100's gotta go. So 35 divided by 100 is 0.35 or 35 hundredths is equal to 1/2 to the power of T divided by 5,700. Okay, so my variable is in the exponent. I need to get rid of the exponent, so I'm going to take the log. What log am I going to take? I'm going to take the log of whatever base I'm given. So this is the base that I was given. So I'm going to take the log base 1/2 of both sides. Log base 1/2 of 0.35 is equal to the log base 1/2 of 1/2 to the T to the divided by 5,700. Again, I need you to walk out understanding. This is asking you 1/2 to what power gives you 1/2 to the T over 5,700. Since my bases are the same, my question mark has to equal to T over 5,700. So on the right hand side, I'm left with T divided by 5,700. And on the left hand side, using the change of base, I get log of 0.35 divided by the log of a half. And how do I get rid of dividing by 5,700 to get the t by itself, excuse me? I'm going to multiply both sides by 5,700. So my final answer for t is 5,700 times the log of 0.35 divided by the log of a half. And if you do that in your calculator, the log of 5,700 times the log of 0.35 divided by the log of a half, it's about 8,633 years old. That's how old that fossil is. Next question here. And again, please feel free to pause. And if you have any questions, please contact me. Number 4. In 2000, the population of India reached 1 billion people. I don't know why that is highlighted. Okay. And in 2025, it is projected to be 1.4 billion. Part A says find the values for C and A so that P of X is equal to C times A to the X minus 2000. And that equation is going to model the population of India in year X. Part B is to estimate India's population in 2010 and use the equation P to determine when India's population might reach 1.5 billion. Okay, so for part A, we need to find C and A. Alright, so we have so far, we want P of X is equal to C times A to the X minus 2000. So we need to find our base, and we need to find our value of C. So a nice little trick here, let me zoom out here. It'd be nice if we could notice that we have X and P of X. And we actually have two values here. So this is 2000. When X is 2000, it's 1 billion. And it's for 2025, it's going to be 1.4 billion. It's projected to be anyway. And so here we can find C first. So let's find C first. Since we have X equal to 2000. Okay. So we have and P of X is equal to 1. P of X is equal to 1. So I'm going to substitute stuff in. So I have 1 here, and I'm going to put it in blue. So 1 is equal to C times A to the 2000 minus 2000. And so I have this 1 that I substituted in here, and I have this other 2000 that I substituted in here. Now the nice thing about this 2000 is that when I substitute it in here, 2000 minus 2000 is 0. And really I'm left with 1 is equal to C times A to the 0. And so that's beautiful because A to the 0 we know is 1. And 1 times C is just C. So C is equal to 1. So if we didn't have this 2000, which is that 2000, we wouldn't be able to find C in this manner. But it works right here. Next one. So now we're gonna find A. So let's find A. Using the second point, 2025, comma 1.4. Okay, so let's substitute stuff in. So I have 1.4 is equal to, the C is 1, times A to the 2025. So that's what I'm going to substitute in. Minus 2000. So this is going to be 1.4 is equal to 1 times anything is whatever's left. So this is going to be A to the 2025 minus 2000 is A to the 25th. Oh, how I wish I was in the classroom, but 1.4 is equal to A to the 25th. The A is not by itself. I have it raised to the power of 25. How do I get rid of that 25? And I know someone's saying by erasing it, but you don't. That's not how you do it. And so the answer is, you can, there's two answers. So I'm going to go ahead and put them over here. They both mean the same thing, but I need you to, again, if math is in your future, to know both of these. So you have option 1 and you have, option number 2. So option number 1, take the 25th root of both sides. So I'm going to take the 25th root of both sides. And so the 25th root and the to the power of 25 are inverses of each other. They cancel each other out. So on the right hand side, I'm just left with A. And A is equal to the 25th root of 1.4. And you can do it in your calculator. And you're going to get that A is approximately 1.0135. Option number 2. Raise both sides to the power of 1/25. So I have 1.4 is equal to A to the 25th. And I'm going to raise both to the power of 1/25. Raise both sides to the power of 1/25. On the right hand side, raising a power to a power, we multiply. So 25 times 1/25 is going to give me power of 1. So A to the power of 1 is just A. And this is going to be 1.4 to the power of 1/25. And if you do that in your calculator, you're going to get approximately 1.0135. All right. So our final answer, now that we've done everything here, P of X is equal to, so our C is 1, so I'll write it, times 1.0135 A to the X minus 2000. Now I'm going to change this to just times, just because. Part B says estimate India's population in 2010. Okay, so P of 2010 is equal to 1 times 1.0135 to the A to the 2010 minus 2000 power. And if you do that in your calculator, you should get about 1.14-ish billion people. Let's see if that is true. Let me get my calculator out here. That's not what I wanted. This is what I wanted. Okay, so let's see. Okay, this doesn't want to work. Maybe because it's sideways. Let's see. There we go. Okay, so let's do 1 times 1.0135, technically x, to the power of 2010 minus 2000, because I don't even want to, I have to make sure, so I need to probably put parentheses here, minus 2000. I get an answer here. Oh darn. I found my A. Why am I writing it again? Major brain fart. Fix this, please. So now my pencil is going really small. Some of you probably caught that and wish we were in the classroom so we can get some points. Wow, this is really slow. Okay, so this is 1.0135 to the x minus 2000. And so this was 2010 minus 2000. So let me take off that x. And it is about 1.1435 people. Billion people. Okay. So that's part B. Part C says use P to determine the year when India's population might reach 1.5 billion. So I'm going to do part C right here. So for part C, I'm going to use the formula. And I could zoom in. What was it? 1 times 1.1435 to the power of x minus 2000. Oh, I was getting the answer. 1.10135. 1.0135. Okay, so I wrote down the equation and we want to know when it's going to reach 1.5 billion. So this is going to be 1.5 is equal to 1 times 1.0135 to the power of x minus 2000. Well, 1 times anything is itself, so 1.5 is equal to 1.0135 to the x minus 2000. And again, my variable is in an exponent. So to get rid of the exponent, I'm going to take the log of both sides using the base that I was given. So I'm going to take the log base 1.0135 to both sides. So on the left-hand side, using the change of base formula, it's going to be the log of 1.5 divided by the log of 1.0135 is equal to just x minus 2000. I'm not going to do my little cloud anymore, but again, the log base 1.0135 of 1.0135 to the power of x minus 2000 is asking us 1.0135 to what power? Gives us 1.0135 to the power of x minus 2000. Well, my answer is x minus 2000. And so if I wanted to get x by itself, I would add 2000 to both sides. So my exact answer, sorry for the background noise. That's my exact answer for x. And if you do this in your calculator, you should get, let's see. So I'm going to do log of 1.5 divided by the log of 1.0135 and then plus 2000. So it should be in the year about 2030. So x is approximately the year 2030 for part C.